All right, guys, more on hypothesis testing. Hypothesis testing for proportion. That shouldn't be proportion test. Just hypothesis testing for proportions is all it should be there. So that's a typo. Guys, this is going to be the kind of video you like. It's going to be a quick one. If you've paid close attention and tattooed all that stuff to the brain that I've told you to do before, this is going to be a piece of cake. Just notation changes a little bit. The biggest thing in being able to succeed at hypothesis testing for proportions is just being able to differentiate them between the mean type of problems and just get the test statistic down. So, guys, hypothesis testing for proportion involves categorical variables, gender, political party, religious affiliation, eye color. Even quantitative variables can be categorized. A lot of times we look at ACT, for example, which is clearly quantitative, not categorical. But sometimes we want to focus on maybe a range, maybe 28 and higher versus 27 and lower. So we can categorize sometimes even a quantitative variable. So anyway, it has two possible outcomes. It has the outcome that possesses the characteristic of interest, and the other is the opposite of that, the characteristic that's not of interest. So again, if we talk about ACTs of 28 or higher versus ACTs of 27 or lower, that again is the way it's presented as categorical variable. So the fraction or proportion of the population in the category of interest is denoted by pi. So let's say we find that or we claim that 22% of students at Shawnee State University has ACT of 28 or higher. So pi would be 20.22, 22%. Sample proportions are given, guys, that should be p hat. This textbook refers to it as p. I still like a sample proportion to be p hat. But that's really what makes statistics so hard for students to learn, is the inconsistencies in the notation. This book uses p and pi for a sample proportion and population proportion respectively. And the other books use p hat and p as the sample and population, respectively. Anyway, they're using p and pi here, so I'll try in my videos to be consistent. So when n times pi and n times 1 minus pi are both greater than 5, this p can be approximated by a normal distribution with the mean and standard deviation that I gave you in the sampling distribution parts. So what's that tell us for hypothesis testing? It tells us that when we conduct one of these, as long as n times pi and n times 1 minus pi are greater than or equal to 5, we use the z distribution. And the z statistic, the test statistic, is calculated by taking p minus pi over the square root of pi times 1 minus pi over n. Now guys, if you're paying attention, that stuff should look awful familiar, because this is the stuff that we studied back in sampling distributions. Now, one thing to note, if n times pi or n times 1 minus pi is greater than or less than 5, it's not discussed in this chapter. We throw those problems out, so don't be concerned with that. So, marketing company claims that it receives 8%. Guys, when you see the population parameter listed as a percentage, that is the cue to you to use a proportion test. If it says an average, average size of a bolt, average size of average hotel cost in New York City, if it says something like that, it's a mean problem. But if it says 8%, so what I know here is the marketing company claims that it receives 8% of responses So 92% of responses it doesn't receive, okay? So to test this claim, a random sample of 500 were surveyed, and there were 25 responses. There were 475 non-responses. So test at alpha equal 0.05. So over in your little blue box there with the check mark beside it, you can see that they multiplied 500 times 0.08, n times pi. They got 40, bigger than 5. N times 1 minus pi, 500 times 0.92, 460, bigger than 5. So we've satisfied the assumptions. Now, first thing I want you to do is concentrate on the test, on the null and alternative hypothesis. So H sub O is pi equal 0.08. That's the hypothesized value. They're testing that it's not equal to 0.08. Alpha is set at 0.05, so our critical values are plus or minus 1.96. And they calculate the test statistic, and they get negative 2.47. Again, that tells us what? Our sample data of 5% response rate is 2.47 standard errors below the claim of 0.08 in our null hypothesis. So negative 2.47 falls in that left tail. So it's lower or to the left of negative 1.96, which is one of our critical values. So we reject the null at the level 0.05, and we say that there is sufficient evidence to reject the company's claim of an 8% response rate. Not only do we reject it, we can conclude that it's lower than the 8%. So p-value solution. Since we have a negative 2.47, we're going to find the area below that. That's easily done in StatCrunch. You guys learn to do that in normal distributions and sampling distributions. We multiply that by 2 because in a two-tailed test we have to account for both tails. And the p-value, total p-value is 0.0136, which is less than 0.05. Which again leads us to reject the null. So guys, you can see how when you get a solid foundation for testing hypotheses actually, whether it's a critical value approach or a p-value approach, it consistently applies to whether we're doing a hypothesis test of mean or a hypothesis test of a proportion. So we get into a little kind of a sidebar here, statistical significance. Anytime we reject the null, we get statistical significance. But guys, it doesn't always mean that we have practical significance. Statistical significance just means that there's evidence to reject the null. But we're going to get into something called power, and power is closely related to the sample size. So when our sample size gets really large, we get a lot of power, which sometimes creates statistical significance but not practical significance. And let me give you an example of that. Let's say that we think at Shawnee State University that the average ACT of entering freshmen in 2019 will be 24. So we go out and we get a sample of 3,000 potential applicants, and we find that we reject the null. But the claim mean of 24, and let's say that our sample mean was 24.1. So we find that our population value is 24.1 versus 24. Now, is 24.1 higher than 24? Yeah, it is. But when we talk about ACTs, we typically talk about 24s and 25s and 23s. So there would be statistical significance there, but there really wouldn't be practical significance because really, who cares 24 versus 24.1? They still, kind of round to an ACT of 24. Says practically important results might be found by statistically insignificant. Sometimes if you don't have enough power, your null hypothesis can be false, but you just don't have enough power to find statistical significance. So I think in some ways this This screen is a little bit premature. I think it's going to be better for you to get some good solid experience with hypothesis testing and looking at power and and seeing what happens when we have statistical significance, but we have too much power where it leads to a failure of practical significance. Gang, that's it. I'm done.